This movie is the first in a series that include a whole bunch of basic information that I'm hoping that you guys will be fluent in by the time you show up here at Caltech in June. First, we're going to cover some of the basics of infrared light. This is one way of looking at the electromagnetic spectrum. On the left here, you can see gamma rays, X-rays, ultraviolet, visible, and infrared light. There are 4 telescopes that have the special name of NASA's Great Observatories. NASA has several different orbiting observatories, but only 4 are special enough to get the name Great Observatory. Compton is no longer with us. It observed in gamma rays. Chandra is still flying. It observes in X-rays. Hubble is still with us, of course, and it observes in the visible. And Spitzer observes in the infrared. This is what you get when you look at the same galaxy in many different wavelengths. Here you have an image that you might take with Chandra in X-rays. Here you have an image in the ultraviolet, which you might take with a spacecraft called Galax. Here is an image in visible light that you might take with HST. Here is an image in the near-infrared, which you might take with TUMAS, which is an all-sky ground-based survey, or Spitzer. Here is an image in the far-infrared, which you might take with Spitzer or Herschel. The wavelengths that we're talking about vary a lot. For X-rays, you have wavelengths that are 2 nanometers or a billionth of a meter. The temperature of the things generating these X-rays are typically about 1,000,000 Kelvin, so we're looking at things that are like black hole accretion disks. In the ultraviolet, we're talking about wavelengths that are maybe 200 nanometers, about 15,000 Kelvin. And these are usually the hot stars, otherwise known as the young stars. In visible light, we're looking at about 500 nanometers, or about half a micron. A micron is a millionth of a meter. We're talking about things that are about 6,000 Kelvin, and these tend to be the run-of-the-mill stars, all ages. In the near-infrared, we're looking at things that are 1,600 nanometers, or 1.6 microns, about 2,000 Kelvin, and these are the very cool, usually old stars. In the far-infrared, we're looking at things that are wavelengths that are 100,000 nanometers, or 100 microns, things that are about 30 Kelvin, which is cool dust heated by hot stars. If you remember from your Astronomy 101 textbook, they might talk about Wien's law. That's the formula that I used to convert those wavelengths to temperatures. This is another way of looking at the electromagnetic spectrum. Here at IPAC, we're a little bit biased. We like the infrared. So here's a picture of a little dog in visible and infrared light. There's 2 really important things to see here. One is that the infrared light is a remapped color image. Sometimes you hear the term false color, and when you're working with the public, sometimes that engenders a sense of mistrust, a sense that we are trying to fool you. We're not trying to fool you. Your eyes don't see infrared light. So if I gave you a true color image, it would be that, which would be pretty boring. So all I'm doing is I'm mapping the infrared light into colors that you can see. And the way that I'm doing that corresponds to a temperature scale as given here on the right. So things that are black, purple are cool. Things that are yellow, white are hot. So he's a fluffy little dog, so there's a halo of fur around his face that is cool. His ears are warm. His face is warm, but because he's a healthy little dog, his nose is cool. So now we know that hot things glow in the infrared. Which one is the hot water? Hot water is the one on the bottom. You can see the base of the faucet heating up and the sink basin heating up. The base of the cold water faucet is still cold even when the hot water is on. And you can see that in the cold water view too. The sink basin is cooling off, but the base of the hot water faucet is still hot. Infrared can reveal things that are hidden in visible light. What do you think this is going to look like? I can tell you the hairdryer is on. That's what it looks like in the infrared. You can see the heating coils. I just love this picture. Infrared, it turns out, can see through some things that are totally opaque to visible light. This is me with a green garbage bag, like what you might put yard waste in, but in the infrared, you can see straight through it. Turns out you personally are incredibly grateful for this property of infrared light, because if you are unconscious in a burning building that's full of smoke, this property is how the firemen will find you. Here on the left, you see a picture of a fireman that you can barely see through the smoke, but in the infrared, he is very obvious, and his breathing apparatus and the things that are helping to keep him cool are quite obvious as well. So if you are unconscious in a burning building, this is how the firemen will find you. If you're an educator and you're looking to borrow an infrared camera for a demonstration, talk to your local fire department, because chances are excellent they have one. Some things that are transparent in visible light are totally opaque in the infrared. These are some French doors in my living room. This one is open, this one is closed. You can see me by seeing straight through the glass in the optical, but in the infrared you can't see through it at all. This, incidentally, is why your car, when you park it in the sun in the summer, gets so hot, because all the visible light comes into the car through the windows, heats up the inside of the car, which then re-radiates in the infrared, and the infrared can't get out through the glass. So the next time you can't touch the steering wheel of your car, think of all the infrared that's trapped in your car. So now we're going to leave the regime of everyday things. Now I'm going to put some frozen peas and liquid nitrogen. Here on the left, we have something called a dewar, which is really just a fancy name for a thermos bottle. And there's liquid nitrogen in there. Liquid nitrogen is at 77 Kelvin, and the camera can't see 77 Kelvin, so it just gives up and colors it all black. Now I'm going to add some frozen peas into the liquid nitrogen. The frozen peas are cold, but they're warm compared to the background, and so the camera can see them. And that's exactly what's going on in space. We're looking at things that are cold but warm compared to the background, and so they glow in the infrared. There's the familiar constellation Orion in the optical and in the infrared. How much you miss if you stick with just the optical. So now let's look a little bit more specifically at the different kinds of infrared light. 1 micron light, wavelength of light, is typically thought of as the near infrared. Optical is over here. By the time you get to about 10 microns, it's typically thought of as mid-infrared. Between 100,000 microns, it's typically far infrared. The boundaries are squishy, and it depends on who you're talking to and, frankly, how they detected the light as to exactly what they call near infrared, mid-infrared, far infrared. But just for scale, optical wavelengths are like half a micron, so that's about the size of a bacterium. Near infrared is about the size of a smoke particle or a pollution particle. Mid-infrared is comparable to the width of a human hair. Far infrared wavelengths are comparable in size to a salt grain. So think about that. That's light with wavelengths the size of a salt grain. That's much different light than you're used to thinking about every day. So as the tip of the iceberg for our discussion on infrared astronomy units, wavelengths in infrared astronomy are commonly expressed in microns or micrometers, which can be abbreviated μm if you want to be formal, or if you don't have a mu handy, UM also works. Visible light, like I said, is half a micron. Near infrared is about 1 to 5 microns. Mid-infrared is about 5 to 30 microns. 30 to 350 microns is far infrared. Brightnesses or fluxes are most likely going to be given in Janskys. This is named for Carl Jansky, so it does have a capital J, and it abbreviates it JY. And it is spelled, the plural of it is spelled Janskys like this because Jansky is a name. You can also find them in millijanskys or microjanskys. 1 Jansky, if you want to convert it to SI units, is 10 to the minus 26 watts per meter squared per hertz. Janskys can be converted to magnitudes, and it used to be that magnitudes were very rarely used in the infrared, but because of all the missions we've had in the past 10 years, magnitudes are now used with gleeful abandon throughout infrared astronomy, and people frequently move back and forth between magnitudes and flux densities. We're going to do that too.